In the last lecture, we have learned how to design the fundamental circuits, means the common digital elements like decoder, the multiplexer, one half adder, the full adder. Now, today we will see how the large complex combinational circuits can be designed using these fundamental circuits, means this half adder, full adder, decoder, multiplexer, or even it can be some smaller modules. Now, the basic concept behind this large combinational circuit design is the design reuse. Now, what do we mean by design reuse? As digital systems are becoming large and large, and obviously they are becoming complex due to different type of applications, particularly the communication applications. Now, it becomes almost impossible to design the whole system from scratch, means the design fundamentals we have read starting from the truth table or the Boolean equations, then the reducing that thing, it is almost impossible. Now, we are very fortunate that studying this behavior of these small large circuits, what we have observed that this large expression which represents the behavior of the complex circuits, that also can be realized by a combination of smaller expressions which are already designed. Now, larger design can reuse the smaller pre-designed module, means that one large equations as if that are partitioned into a smaller set, a number of smaller equations. Now, these equations can be realized by the rule we have read or the design rules we have already learned. So, they are already some modules are already designed. These modules we are telling as if these are some fundamental circuits that already we have learned. Now, using these modules, these are the pre-designed modules, that means we can now design a big circuitry. Now, for these large complex designs, as if the components are not the gate, not the AND or NAND, this type of gates, rather they are replaced by half adders, full adders, marks, decoders. These we are calling as if the reusing of the circuits or the fundamental circuits or the digital common digital elements. Now, what will be the rules for this complex design? Already we know that the simpler design how we can develop. Now, use fundamental circuits called the basic building blocks, as if these will be treated as the basic gates. So, the basic gates are now replaced by basic building blocks, where these building blocks are there. The already what we have read, that our half adder, our full adder, the decoder, the encoder, and particularly the marks, and they can be any other smaller modules. Now, this reuse basic building blocks to design new circuits. So, as if these smaller circuits or what we have defined that basic building blocks, they are pre-designed, pre-verified that they are working correctly. They are realizing the small expressions or the equations correctly, and then we can use these building blocks to design the complex circuits. Now, use a hierarchy, that means here we can use or the concept of hierarchical design. of such hierarchical design, last day we have seen when a larger marks multiplexer we have designed from the one smaller multiplexers. We call that this is a multiplexer tree, already we have read that thing. Now, as the circuits are large or the systems are becoming complex, now almost it is impossible to do this design or to develop the system manually. Now, for these purposes we use the CAD tools, the computer aided design tools. Now, first we take one very simple example, that one 9 input odd parity generator. Now, design a circuit with 9 inputs and 1 output. How we are defining the parity generator? If number of ones in input is odd, then we call this is a odd parity, or then output is 1. And if the number of ones are even, then the output will be 0 and then it will be called the even parity. So, we are defining the parity as if the total number of, depending on the total number of ones in its input, and accordingly the output will be defined. So, if I take one 9 variable function, say f, and see here, if we give a, b, c, d, e, f, g, h, i, these are the 9 variables, then h and I are 1 1, means there are 2 inputs which are true, means 1. So, if it is this equal to, if it is even, then the output will be 0. Now, if the number of inputs are 1, see here a, c, e, there are only 3 inputs which are true, that means here if it is a, c and e, these are 3 inputs. So, these are odd number of inputs are 1. So, the output will be 1. These we are defining as a odd parity. Now, what about the truth table? It has, as it is a 9 variable function, so it has 2 to the power 9 equal to 512 such rows, and 50% of these will have an odd number of ones. So, 256 mean terms, there will be 256 mean terms, means if again if we explain, see there are, we have taken a function f of 9 variables a, b, c, d, e, f, g, h, I. Now, if I draw the truth table, then these 9 variables, they will be 0, 0, 0 to all 1, all possible combinations I have to take, all possible combinations I have to take. Now, if we see that here this will be, it will be 512 2 to the power 9 equal to 512 combinations. Now, these 512 combinations, there will be 256 such cases where, means the half of the cases, 256 means actually 2 to the power 9 by 2, half of the cases it will be odd input, odd means output is 1, as we have defined the parity odd, and it will be even parity, it will be even parity, output is 0. So, if I draw the Carnot map, then in the map it is a 9 variable function map. So, there the number of min terms for the odd parity will be 256, because we will be getting 256 1, and so 256 min terms will exist. Now, it turns out that all min terms are prime. Now, conclusion is that 9 into 256 is 2304, that number of literals will exist. Now, again if we remember our XORs, we see that what was our XOR function. See, our 2 input XOR function was, or the two, if we write the truth table of XOR, this is a 2 input XOR, say AB output is O. Then if it is 0 0, output is 0, if it is 0 1, output is 1, 1 0, output is 1, 1 1, output is 0. See that these two cases where the inputs are even, then output becomes, output is 0. But here these two cases, see the number of inputs are odd, only one inputs are odd. So, output equal to 1. So, a 2 input XOR can be treated as a 2 variable odd parity function. This can be treated as a odd parity generator. For 2 inputs or 2 variables. Now, if we observe the 3 input XORs, what we will be seeing, that if we change, if it is 3 input XOR, then if we take all the combinations, say output is Z, then it will be zero, then 1 0 0 if I take, it will be 1, 1 0 1 it will be 0, 1 1 0 it will be 0, 1 1 1 it will be 1. 1 we have missed, that is 0 1 0 2, there also it will be 1. Now, see there are, here there are 2 to the power 3, there are 8 combinations, 2 to the power 3 equal to 8 combinations. From there, that there are 4 cases, means the inputs are, when the inputs are even, then output equal to 0, and there are 4 cases, then it is giving the output odd, or that means if inputs are odd, means total number of ones in the input combinations are 1, then output equal to 1, which is our definition of the odd parity generator. So, one 3 input XOR, that is a 3 variable odd parity generator. So, already we have read that this is nothing but a that mean terms where if we draw the Karnaugh map that 1, 2, 4, 7 these 4 mean terms will exist. Now, such functions are special, they are called the odd functions, because they are generating, as just now we have discussed, they are generating that the output 1 for input combinations odd, means odd weight, means the number of ones in the input combinations are odd. Now, if we see the Karnaugh map, if we draw that it is a 3 variable function x, y, z, we draw this is x and this is our y, z, then this will be 0, 0, 0, 1, 1, 0, 1, 1. Now, this is 1, 1, 1, 0, 1, 1, 1, 0. See here, for these two terms z is true and this two term y is true. Here x is true, means x equal to 1, here it is 0. Now, see this mean term is nothing but x, y bar, z bar, this is my the first mean term. This is the x bar, y bar, z, this is my second mean term. This is x, y, z, my third mean term, and this is x bar, y, z bar, my fourth mean term. So, this realizes our XOR functions. Now, this is the parity generator, that P equal to x XOR y XOR z. Now, what will be the parity checker? The parity checker will be that if with the parity generator, if I compute the XOR functions and we see that if it is equal to 0 or equal to 1, that means if it is same parity, then it will be giving 0, it will be a different parity, then it will be giving 1. So, this same circuit or the XOR circuit can be used as a parity generator as well as that can be used as a parity checker. Now, if we see that circuit, that for the 9 input parity generator circuit. So, as already we have seen that it is a for the 3 variable, it is a 3 input XORs. So, if it is a 9 input parity generator, so it will be a 9 input XOR functions. So, if I draw the circuits, see there are x0 to x8, these are my input variables, these are my inputs. Okay. So, these are 9 variables, and everywhere I am using a 2 input XORs. See here this is designing a 4 variable XORs. So, if we partition the circuit, this is a 4 variable and the lower portion, this is a 5 variable. So, this is a 4 variable and this is a 5 variable, and then again another 2 input XOR has been used, which is producing the output Z or the odd parity. This is my it is generating my odd parity. Now, see, we have taken this 9 variable as if this is a 3 variable XOR functions. So, if we redesign that thing, see if we redesign, see here this is a logic diagram for the 3 variable odd parity. A0, A1, A2 are the 3 inputs and B are the output. So, if now these we have just redraw that thing as if this is one fundamental circuits I am defining, or this is one module. This module have 3 inputs A0, A1, A2 and one output say B. Now, to design a larger circuitry or to design a larger variable parity generator, I can reuse this module as a basic building block. So, this is my basic building block for designing the larger variable parity generator. So, this is my basic building block. Now, in this second figure, we have redrawn these circuits using this thing. So, if we say this is my basic building block, block 1, my block 2, this is my block 3. And another 3 input building block we have used. The output is the parity generator and these inputs are the 9 inputs of the parity generator, which I want to compute the parity. So, this is the simple concept of the design reuse, that means one 3 input XORs or that 3 variable parity generator first I have designed, and then using these smaller modules as if this is my basic building block, again I am designing the larger variable parity generator. Now, this concept we want to utilize further. Again, another design example we have taken that is very common as well as very important in real life design, that is called the multiplier design. Now, before we start the multiplier design, again we recapitulate quickly our half adder and full adder circuits. We remember that our half adder circuits are that there are 2 operands and we neglect the carry input, and sum is defined as the A XOR B and the carry generated will be the AND of A and B. So, C equal to A B and C equal to A XOR B. Now, these we can this can be treated as a half adder module. So, this is my half adder module or basic building block whose inputs are 2 inputs only, A and B, and there are 2 outputs, the sum and the carry. Now, we want to utilize or use this basic building block of half adder for larger designs. See how it works. Now, consider one 2-bit multiplier. Okay. See that we want 2-bit multiplier, and the two operands are A and B. So, this is A is A0 A1, B is B0 B1. Now, we are multiplying these two. So, from our simple multiplier rule, we will multiply in this way. This will be A0 B0, it will be ANDed, then it is added with, or the next term will be, better we first we compute the terms. This will be A0 B0, second term will be A0 B1, then it will be shifted left in one place, 1 bit shift, and the next term will be A1 B0 and then A1 B1. Now, we take the sum of the terms. So, the first term will be A0 B0, means our S0 is A0 B0, S1 will be A0 B1 plus A1 B0, S2 is as it is A1 B1, and as there is no carry for this particular multiplication. So, S3 is 0. So, we can write now that the terms or expression for S0, S1, S2, S3. So, as already we have defined, S0 is A0 B0, S1 is the least significant bit of add A0 B1 A1 B0. See that this is the two terms, this is one summation. S1 is the, or S1 is the A0 B1 sum of A1 B0. So, the sum of the two terms will be actually S1. Then what will be my S2? S2 is the second bit of A0 B1 plus A1 B1 and A1 B0. See, this is that S2. S2 means the sum of the third term and the carry of the second term. So, that is written here, and for this case there is no S3, but for some multiplication S3 can be there. So, if we now see that what will be our S0? See, our S0 is simple A0 B0. So, A0 B0 means one simple AND gate. So, this is my AND gate, and see that A0 comes, this is my A0, A0 is one input and B0 is one input. So, this is A0 B0 is S0. So, A0 B0 is S0. What is my S1? S1 is the two terms will be added and the sum of that. See, first we have to add A0 B1. So, this is the AND gate whose inputs are A0 and B1, and the output is fed to a half adder. Now, this is one half adder. We need half adder module whose two inputs are, one is A0 B1, other is A1 B0. So, this is another A1 B0. So, this is A1 B0 is the output of one AND gate whose inputs are A1 and B0 itself. So, this is one half adder module. Now, another half adder I need whose that the carry of the previous half adder, the carry of the second terms, that is one input and other one is the A1 B1. So, A1 B1 is coming from a 2 input AND gate whose inputs are obviously A1 and B1. And this is sum is S2, and if there is one carry, then that is my S3. So, the product is S0, S1, S2, S3 we are getting from here. Now, see here there are 4 AND gates, 4 2 input AND gates. We need 4 2 input AND gates and 2 half adder. So, these half adders are used as the basic building blocks for a 2-bit multiplier. Now, we see a larger multiplier and see whether the half adder will be sufficient or we need some other basic building block. See here, if we multiply the 3 bit, that means A0, A1, A2 to B0, B1, B2, then actually B0, B1, B2 we can write as if these are the combination of 3. So, 0 0 B0, 0 B1 0, B2 0 0, because these are the LSB is B0, the second bit is B1 and the MSB is B2. So, as if we can partition or we can break the B2, B1, B0 as the 3 different combinations, and then if we add it will be B2, B1, B0. Just if we take an example, say if it is 1 0 1 1, then see our I can break that 1 0 0 0 0 0 1 0 0 0 1. So, 0 0 0 1 means this is decimal 1, 1 0 means 2, this is 8. So, 8 2 1, this is actually if we this will be 11, or 1 0 1 1, that is also my 11 in decimal. So, these two are same. Now, this concept is being utilized in the larger multipliers. Now, before again we see that larger design of the multiplier, again we recapitulate the full adder circuit. Now, the full adder, as we remember, here the two with the 2 operands, another operand is there which is the carry in, because that as it is a set again a 2 bit adder, if we consider, previous bit carry is also considered because it is doing that sum. So, S is Ax or Bx or C, C is AB plus BC plus CA. Again we can design this thing as if this is a full adder module whose inputs are 3 A, B, C and outputs are sum and carrying out. So, now this full adder can be utilized as the basic building block of the complex circuits. Now, we take a 4-bit multiplier, say some B3, B2, B1, B0 and the multiplier is a 3-bit multiplier, say A0, A1, A2. So, we are taking a multiplier that B into A, where B is B3, B2, B1, B0 4-bit, whereas A is 3-bit A3, A2, A1, A0. Now, if we multiply, see that the similar way that we have already we have done that multiplication. If we see, okay, if we take that example, that multiplier, say what we want, B3, B2, B1, B0 and we want A2, A1, A0 to be multiplied with this. Again there will be some terms, it is A0, B0, then this term will be A0, B1, then A0, B2, then A0, B3. Now, when it will be multiplied by A1, it will be shifted by 1 plus. So, it will be A1, B0, A1, B1, A1, B2, A1, B3. Again, it will be shifted when it will be multiplied by A2, A2, B0, A2, B1, A2, B2 and A2, B3. Now, we have to add the whole thing. So, A0, B0 will be as it is. So, this will be this thing. Now, these two terms, they will be added as A0, B1 plus A1, B0. See, there will be no, for the second term there will be no carry. Now, for the third term, see, for the third term it will be A0, B2 plus A1, B1 plus A2, B0 plus the carry coming from the second term, Similar thing will happen when we will consider the fourth sum. This will be A0, B3 plus A1, B2 plus A2, B1 plus the carry coming from the third term. So, we can just as if this is the carry coming from here, here the carry coming from here, Similarly, here the carry coming from here and the sum, and here the carry coming from here and the sum. So, this way we can write this thing as if these are my sums. So, now we have to develop a circuit for which will be doing this AND means multiplication as well as the term multiplication as well as the sum of the terms. Now, see this my A0, A1, A2 are the 3 inputs, the multiplier, and these are the B inputs, the multiplicand. So, this is my B multiplicand, the 4 bits. Now, see that okay. That this output of this AND gate, this is A1 B3. So, output of this AND gate is A1 B3. Similarly, this will be A1 B2, this is A1 B1, this is my A1 B0. Now, this term is A0 B1, A0 B2, A0 B3 and A0, another AND gate is there which is simply computing A0 B0, my first term. We remember the first term is, this was my first term, that A0 B0, it will be as it is. So, this is my A0 B0 term, that it will be as it is, giving the output of or the LSB of the output. So, this is my O0. Now, what was the O1? See, O1 was A0 B1, A1 B0. You see, so O1 is coming that where that one input is A0 B1. So, this is my A0 B1 and this is my A1 B0. So, it is a 4 bit full adder whose the 2 LSBs are added and there is no carry in, the carry in is 0. So, it is simply giving that A0 B1 plus A1 B0. So, this is my the second output bit O1. Now, see now as it is a full adder, that means that carry of this sum, it is propagated to the second bit. So, now there is one carry, say C1. Now, if we see the second term, see here the A0 B2, A1 B1, A2 B0 all are added with the carry from the second term, and these are A0 B2, A1 B1. See, these are A0 B2, the second term, and this is the A1 B1. So, A0 B2 and A1 B1 see this is my A0 B2 A1 B1 plus my carry. Now, these are added, another term is there. What was the another term? That is my, see, still this value is left A2 B0. So, I have to add A2 B0 also. So, this is, what is my A2 B0? Because this is one term, and see the LSB of the, this is a add 4 bit adder, another is, this is my A2 B0. So, this is my A2 B0. So, A2 B0 and this it will give my O3. So, 2 full adder, 4 bit full adder we are using, where the LSB of the first adder with the carry from the previous term is fed as the LSB to the next full adder, and the LSB of the multiplicand is the other term left, that is the A2 B0. Now, similarly for the fourth term, we see that carry coming from the third term plus A0 B3, A1 B2, A2 B1. We see that again this is my A0 B3, this is my A0 B3, and second term is, this is my the third one is A1 B2. So, this is A1 B2. Now, A0 B3 and A1 B2, see this is A0 B3 and A0 B3 and A1 B2, these are added with the carry C2. Now, they are feeding as the third one, means they are going here. Now, this term, this is my another term is left, another term is A0 B3 A1 B2 is already considered, another term is A2 B1, carry is also considered. So, here see now that A2 B1, the second term, here this is my second one, this is my second bit, and here A2 B1, that is also second. So, for the next 4 bit full adder, that second the second bit, it takes a summation of the second bit. So, this is one and this is another. So, it will be giving the O3, and similarly the O4 and O5, they are also being generated. Now, mainly what we want to show or we study from this circuit, that we are actually designing a multiplier, a 4 bit multiplicand, a 3 bit multiplier. Now, just to do that thing, we are using some AND gates, some basic gates and 2 4 bit full adder. So, these 4 bit full adder we are defining as if these are my 2 basic building blocks or 2 pre-designed module that I am reusing here. So, these are some fundamental circuits. Full adder is a fundamental circuit. I am using that thing in my larger designs or complex designs. Now, so far we have seen that two examples where we have used one simple smaller circuits, a 3 input XOR, a 4 input XOR. that can be treated as a module, and they are being used as the basic building block of the larger circuits. Then we have studied multiplier. If it is a smaller 2-bit multiplier, my half adder can be a basic building block. If it is a 4-bit multiplier, my full adder circuit can be a basic building block. Now, there are many other fundamental circuits: decoder, multiplexer, encoder, demultiplexer. Now, one such example we see where the decoder can be used as a basic building block, and the example is, or the design is, the binary to gray code converter. So, we want a circuit, the problem is we want a circuit where the input is binary and it will generate the output, which is actually the gray code, means the gray code, there is one property, unique property is there, that it generates a unit distance, it maintains a unit distance from to its previous one. So, just we see here, there is, that means I want, better I draw, I want a design, say this is a black box whose inputs are A, B, C, D, A, B, C, D, outputs will be W, X, Y, Z. So, as there are 4 inputs, I am giving 0 0 0 0 to 1 1 1 1, that 16 such combinations. Then for 0 0 0 0, it is say again the output, the 4-bit output W X Y Z are 0. Then that 301 0 0 0 1, again output is 0 0 0 1. Now, see that here that distance is 1. Now, distance we define that number of places it varies. See here that the previous one is all 0 and the next one varies in one place only. So, here the distance is 1. Similarly, that when it is 0 0 1 0, this becomes, see that now the output changes, the output becomes 0 0 1 1. So, that again it maintains a unit distance from the previous one. When it is 3, again this becomes 2. So, that it continues, that property is maintained. So, in this way we can generate that see this is a 4-bit for gray code generator. So, and if we observe the outputs W X Y Z, the patterns of W X Y Z, we will be seeing that always that it maintains that property, that always unit distance is maintained from the previous one. So, between 2 consecutive patterns of W X Y Z, always the distance becomes 1, that means the number of places it varies is 1. So, now I want to design this type of circuit. Now, if there are 4 output lines W X Y Z, so the output expressions if we write, it is will be seeing that these are, see for if we just see that W, then W, that W will be 1 for when ABCD values are 8, 9, 10, 11 up to 15. Similarly, X, Y, Z are there. So, we can write the output expressions that W becomes 1 when these min terms exist 8 to 15. Similarly, X will be there 4, 5, 6, 7, 8, 9, 10, 11, 12. Y will be 2, 3, 4, 5 and again 10, 11, 12, 13, Z is 1, 2, 5, 6, 9, 10, 13, 14. Now, if we draw the Carnot map, and as we know that we can reduce the expressions for the 4 outputs. So, the circuits will be like that. See, these are my W, X, Y, Z. These are my four outputs W, X, Y, Z. If we observe, the inputs are 8 to 15. These are the decimal value I have written, and the ABCD inputs are given, then accordingly that these outputs will be generated, which is fed to the that WX YZ generator. See here, this is a decoder, this is a 4 to 16, that means 4 to 2 to the power 4 decoder that we are utilizing to design this type of circuits. So, when these ABCD values will be 8 to 15, means 1000 to all 1, then my W will be generated. That it will be fed to the input of the W. Similarly, when ABCD value will be any one of these, means 4, 5, 6, 7 and 8, 9, 10, 11, 12, then it will be Y will be generated, and similarly X and Z will be generated. So, here decoder is used as the basic building block. So, in this way that larger complex circuits can be designed from the smaller modules. Okay, we end this lecture here, but we will continue this for another different other variety of examples. Thank you. In the last lecture, we have seen how the complex combinational circuits can be designed using fundamental circuits. These fundamental circuits mean we have considered half adder, full adder, the decoder. Now, today we will read how the combinational circuits can be designed using another fundamental circuits called multiplexer. Now, already we have read the functions of multiplexer, but again quickly